Okay, uh, let's look at some of the properties now of this cis theta. Okay, cis being cosine theta plus I sine theta. Okay, there are some useful properties or rules that pertain to this function. Okay, so cis theta times cis phi, if I have two different cis expressions with different angles, and I multiply those two cis functions together, what happens is I can simplify that, combine those, and write it as cis of theta plus phi. Okay, we will show this in later on in this section. Okay, cis of theta all over cis of phi is also cis of theta minus phi. Okay, and you can see that these two are sort of like, okay, not exactly, but sort of like properties of exponents. Okay, where if I have a to the x times a to the y, multiplying those two expressions, I add the two exponents. Here I'm adding the two angles. Okay, and same thing with the division. A to the x over a to the y is a to the x minus y. Likewise, cis theta over cis phi is cis of theta minus phi. Okay, and since we're talking about cosines and sines, and you know how they're periodic, well, the cis of theta plus 2 pi times some multiple where k is an integer, multiple k or k is an integer, that can be reduced, that angle can be reduced into the desired angle where it's between minus pi and pi, and we can write it as cis of theta. Okay, so we can simplify these large angles into smaller ones. All right. So let's just do some quick examples here. This is very, very easy. Okay, let's simplify this expression. Okay, so cis, we know from our property that the product of these two expressions can be combined into one, and we would write this where the angles are being added. Okay, so that's it, and then we just multiply by 2, simplify that, so that's 5 pi over 10, so that's pi over 2. Okay, cis pi over 2. I'm not totally done here because I could simplify this more. Sometimes it's more useful to write it in component form, sometimes it's more useful to write it in polar form, but let's just write this in component form. Okay, where is cis pi over 2? Pi over 2 is up here, right? Okay, pi over 2 is here, so now I just need to determine the length. The length is 1, right? It's 1 cis pi over 2. So it would be on my imaginary plane, and here's my real, imaginary axis, real axis. And so this is 0, 1. So that would be the vector 1i. Okay, so that would just be I. All right. So what about cis pi over 5 minus cis 7 pi over 10? You get the idea. Okay, I'm going to skip this one. You could do the same thing, and then just draw your picture and try to write that in terms of in real and imaginary numbers. Okay. Simplify 107 pi over 6. Okay, so here we have a large angle. Let's get this into a smaller angle. Remember we said cis of theta plus k times 2 pi, okay, can be simplified into cis of theta. So that's what we're going to do. Let's try and get rid of this. So if I do 107 pi over 6, that can actually simplify into, okay, that if I divided 107 into 6, I would get 17 and 5 over 6 pi. Okay, so now I want this number to be an even number, okay, because if it's an even number, then I can divide by 2 and get rid of all the multiples, right? So I'm going to rewrite this as 18 pi. This is the same as 18 pi minus pi over 6, minus 1/6, right? So now I can get rid of this guy because this is divisible by 2 pi. Okay, so cis of 107 pi over 6 is the same as, if I get rid of this part, cis of minus pi over 6. Okay? So cis of minus pi over 6 then on my plane would be down here, okay, where this is minus pi over 6. My magnitude is 1, which is nice. So what are the coordinates of this point? This is 30, so that would be 1/2, and this would be root 3 over 2. So it'd be root 3 over 2 and minus 1/2. So this would be root 3 over 2 minus 1/2 I. Okay? So pretty simple. This is my real part, this is my imaginary part. It's just writing the components with the I there. Okay? This is an interesting one. Use the properties of cis theta to find the transformation that moves z to iz. We've already done this, right? We did this in the previous section. We know that I will result in what transformation? If I multiply by I, we know that that's going to rotate it counterclockwise pi over 2, right? Okay, so using the properties of cis theta, go ahead and try this. This is example 13 in your book, okay, number 13 in your book. So try this first, see how I could use the cis properties to get here. Okay, I'll give you a head start. Z equals r cis theta, and now use I is cis pi over 2. Oops. Use this property, multiply these two and see what you get, okay? Now, multiplication of complex numbers. Okay, if I have two complex numbers and they have different moduli being the plural of modulus, okay? If they have different moduli and they have different angles or arguments, and I multiply those two together, okay? This is really just a proof of the property that we talked about before, where we have cis theta times cis phi. But this shows you how that happens. Z times W, the multiplication of those two complex numbers, then results in this expression, right? And if I rearrange those terms, Z modulus Z times modulus W times cis theta plus phi. Okay, sorry, it's not a proof, it's just using the property that was given to us before. So once I have this, this is the modulus of z. So what happened to the modulus of z when I multiplied it with w? The modulus of z was multiplied by the modulus of w, and the argument of z, which is actually theta, was increased by the argument of w. Okay, so this is very useful because I can take any complex number, okay, multiply it by another complex number, and what I'm doing then is I'm going to be adding the new angle to my original angle, and taking the new modulus, multiplying it to my original modulus. Okay, so if a complex number z is multiplied by r cis theta, where z is a complex number, right? The modulus of z is multiplied by r, which is the new modulus, and the argument of z is increased by theta, which is the new angle. Okay, so let's try an example here. Example 6. Write z equals 1 plus root 3i in polar form. Okay, so what's that going to look like? Z equals 1 plus root 3i in polar form. Okay, again I'm going to draw. That's positive, so it's in quadrant 1. 1 and root 3. Okay, root 3 is bigger than 1, so we're going to have 1 root 3. Well, that's really easy. That's 2. Okay, so what's my angle here? This is a 30, 60, 90 triangle. So this would be, this side's bigger, so that's 60, so that would be pi over 6. So I could write this as z equals 2 cis pi over 3. Okay, because pi over 3 is the angle there. So that's very straightforward. Okay, now multiply z by 2 cis pi over 6. Okay, so multiply z, 2 cis pi over 3, multiply that with 2 cis pi over 6. What happens there? Okay, so this, we just multiply the argument, moduli, so that's 4, and we take the angles and we add them together. So pi over 3 plus pi over 6, that's times 2, so that's 2 plus 1, that's 3. 3 pi over 6 is pi over 2. Okay, and what is cis pi over 2? Cis pi over 2 is just going to be that, right? And it's actually going to be the imaginary number I. So this is just I. So that becomes 4I. Okay? Very nice. Now illustrate what happened on an argand diagram. Okay? Well, if I were to draw my argand diagram, and let's write my original vector here. This was 2, okay, where this was pi over 6. This was my original vector, and I took the vector, sorry, that would be pi over 3, isn't it? Pi over 3. I took my original vector and I multiplied it with I. So if I multiply it by I, okay, if I multiply it by I here, what happens is this vector increases by 2. It doubles, okay? So it actually doubles, and it's rotated by an angle of pi over 6. So we add pi over 6 here, so that total becomes pi over 6 plus pi over 3, which is pi over 2. Okay, and so this is my new vector, that my new complex number. Okay, so that's what's happened in this. Okay, and then for part D, what transformations have taken place? So now it's just saying what's happening in words. Okay, you could say the modulus of z, okay, was multiplied by 2, so doubled, and then the argument of z was increased by, sorry, my handwriting is kind of messy, by pi over 6. Okay, so that would be making sense of what's happened here. All right. Use complex numbers to write cosine 7 pi over 12 and sine 7 pi over 12 in simplest surd form. Okay, this is kind of a tricky one. Cosine of 7 pi over 12. I want to write that in terms of something with radicals in it. Okay, some expression with radicals and numbers in it. And I want to write sine of 7 pi over 12 in some sort of expression with radicals in it. Okay, now you may be wondering why do this. Okay, this is just an exercise to see your understanding of complex numbers. So try to use the idea, try to get this in cis form. I'm not going to do this for you, it's in your book, so you can try it. Try to get this in cis form and then play around with it and see if you can get it in terms of radicals. Okay, so here's a hint. This is your hint. That's one hint, and your second hint is 7 pi over 12 is not a nice angle to work with, so get it into 2 or 3, however many angles you need, where I do know how to use 2 angles that I do know how to use, and find the cosine and sine of very easily. Okay? Alright, example 8. Alright, let's stop here and we'll finish off in the next video.